If you've spent any time tracking the world of modern AI, you know that the transformer architecture is just, well, it's just dominant.
Completely. It's the foundation for every powerful large language model out there.
And it's a genius design. Its core mechanic, the attention mechanism, lets it scan these huge amounts of data simultaneously.
And figure out which pieces of information are relevant to whatever word it's processing at that moment.
Exactly. But for all its brilliance, the transformer has a very specific and a very persistent Achilles heel. And that is deep, long-range sequential reasoning.
Yeah, that's the word.
Think about reading a massive technical document or debugging a really long piece of code.
Or even just following a complicated recipe.
Right. The meaning doesn't just rely on the words themselves. It's about tracking the state, what happened, what changed, and the precise order it all happened in.
And that's where current models can, they just lose the thread.
So today, we are doing a deep dive into some genuinely groundbreaking research. It's coming mainly out of MIT and their collaborators, and it introduces something called PaTH attention.
And it's a big deal.
It really is. The whole development aims to solve this state tracking problem by giving models this profound new kind of memory for sequence. It basically redefines how they understand order without, and this is key, without sacrificing speed.
Which is the whole game.
Okay, let's unpack this.
It's such a critical problem, and you really hit on why the core challenge exists. Attention is inherently parallel.
It's designed to look everywhere at once.
Exactly.
Yeah.
It's fantastic at identifying associations between words, but it doesn't naturally know or even really care about the physical order they appear in.
So to use your analogy of, say, tracking movement, attention is like a floodlight.
I like that.
It just illuminates the entire room. You see all the objects at once.
But you don't see the path someone took through the room.
Right. If you were tasked with tracking a complex action like moving a chess piece across the board and making several moves based on the state of the game, you don't just need the final positions.
You need the trajectory, the history of every single shift to understand why that final position even matters.
And current systems just give you the before and after picture.
So the initial and the final snapshot, yeah.
So because the original transformer was basically blind to position, researchers had to patch it right away.
They did.
They created these position encoding methods. They're essentially ways to mathematically inject where information back into the sequence.
It's like telling the model, hey, this is token number 5, and that one way over there is token number 500.
And the most successful version of this is something called rotary position encoding, or ROPE.
Right, and ROPE is really clever because it doesn't try to define absolute positions. It just focuses on the relative distance between any two tokens. How far apart are A and B?
Which sounds super intuitive, and it's why ROPE is so popular.
It is. It works great for shorter, more casual language tasks.
So if it's so widely used, what's the hard boundary? Where does it fail when things get really long or logically complex?
The boundary is that ROPE's position math is static.
Okay.
It's a fixed calculation. It's only based on the distance. So if you have 10 tokens separating word A and word B, the mathematical relationship is identical.
Regardless of what those 10 tokens are.
Exactly. Whether they're just meaningless filler or whether they contain 10 critical state changes that flip the entire meaning of the document, ROPE doesn't know the difference.
Ah, I see. So that's where it fails to track the evolving state.
If the relationship between two things changes drastically, say, an object changes ownership, ROPE doesn't care. It only measures the distance.
It completely failed to account for those context-dependent shifts.
The ones that build up along that path. The relationship between those two words is mathematically fixed, even when the semantic context has evolved dramatically.
So the challenge, as one of the senior authors, Yun Kim, described it, is that this positional approach is a bottleneck. We need the model to get not just where things are, but what happened between them.
And we need to do it while keeping that insane speed of the transformer. You can't just accept an exponential slowdown to get a better memory.
Which is precisely why this PaTH research is so exciting.
Exactly.
And that brings us to the core innovation, PaTH attention, which stands for Position and Trajectory History.
A great name.
It is. Instead of treating the space between two tokens as just an empty, measurable distance, PaTH completely redefines that space. It treats it as a substantive, meaningful path.
It's moving from static geometry.
Right, from just measuring miles.
To dynamic, content-aware tracking.
I love the analogy they use. It's like switching from a car's odometer to a full GPS tracking system that logs every turn, every traffic jam, every change in elevation.
And this is where the underlying mechanism is it's fascinating. PaTH doesn't just calculate a distance, it models the journey between any two tokens as a sequence of small data-dependent transformations.
So the positional info isn't just static data you inject at the start.
No, it actively accumulates as the model moves through the sequence,
Oh.
token by token.
Okay, let's try and break down the technical side a bit without getting totally lost in the math.
For sure. So each small step along this path, each token the model passes, applies this mathematical operation. It's called a householder reflection.
Householder reflection, that sounds intimidating.
It does.
But the paper called it a tiny mirror that shifts based on the actual content. Can you maybe elaborate on how that mirror actually works?
Yeah, I can try. So think of the normal positional encoding. It's usually a vector, just a point on a map. With ROPE, the model looks up the distance calculation. It's always the same answer for the same distance.
Fixed, static.
Yeah.
Got it.
With PaTH, as the model reads token 1, that token's content, its actual meaning, is used to reflect the positional encoding. This reflection, the householder transformation, it slightly shifts the positional information.
Right.
Then when it moves to token 2, that new token's content reflects the already shifted position again. It's a cumulative process.
So the positional vector is being constantly transformed and updated by the actual meaning of the words it's passing along the way.
That's it, exactly. The positional memory is no longer a static measurement. It becomes a record of the semantic journey.
So if you hit 5 words that all relate to a major change in the subject's status,
those 5 sequential, content-dependent reflections will fundamentally alter the positional memory. This is what allows the meaning to truly evolve and for state changes to be tracked across massive distances.
now, if I'm hearing this right, that sounds way more complicated computationally.
It is.
A series of cumulative matrix transformations for every single pair of tokens. That should bring the whole system grinding to a halt. It defeats the purpose of the transformer.
And that was the biggest hurdle they faced. And solving it is their second major innovation.
They knew if it couldn't run on existing hardware at scale, it was basically irrelevant.
Right. So to maintain efficiency, the researchers developed a very specific hardware-efficient algorithm.
Here's where it gets really interesting.
It is. This algorithm figured out how to mathematically compress and break down those long chains of cumulative transformations.
A shortcut.
It's a trick, yeah. It lets the model summarize that whole complicated positional path very, very quickly, making sure the whole thing stays perfectly compatible with the speed of GPU execution.
Wow. So that's what makes it a viable technology. It solves the complexity problem, but keeps the real-world requirement for speed.
Precisely.
Okay, let's talk results. What happened when they stress-tested this against models using traditional ROPE?
Well, they designed tests specifically to break the traditional methods. These weren't your general chat tasks. They were targeted stress tests for sequential integrity.
Like what?
For instance, they had the model track the state of a simple system. It would read a series of write commands, and the goal was to recall the most recent piece of written data.
And standard models struggle with that.
They do, especially when you inject dozens or hundreds of irrelevant tokens distractions between the commands.
Ah, because the static positional distance of ROPE means those distractions just dilute the signal?
The model forgets the current state, but PaTH, because it's tracking the actual content path, it successfully navigated all that noise and maintained the state tracking perfectly.
And they measured performance with metrics like perplexity. For anyone who's not an expert, what does improving perplexity mean in real terms?
Perplexity is just a measure of how surprised a language model is by the next word in a sequence.
So high perplexity is bad.
Very bad. It means the model is unsure, it's surprised, it's a poor predictor. Low perplexity means the model is confident and accurate. And PaTH significantly improved perplexity.
Because its superior sequential memory meant it was less surprised by where a complex sequence was logically going.
It knew where the state was headed. And beyond that, it showed a generalized improvement. It performed strongly on reasoning benchmarks it was not explicitly trained on.
That's a huge sign of a real architectural improvement.
It is. And maybe most critically, they showed that PaTH remained incredibly stable, even with inputs stretching to tens of thousands of tokens.
So it's robust, long context reliability.
Exactly.
So we've got a system that's more accurate, more reliable at massive scale, and it keeps its efficiency. But the team also introduced a secondary idea that makes this feel, well, a lot closer to human intelligence.
You're talking about the forgetting transformer, PaTH.
Yes, PaTH. This is where we stop talking just about remembering and we start talking about managing memory.
Mm-hmm.
PaTH lets the system selectively downweight information that's older or just, less relevant to the current task.
Which is how we think. We don't just accumulate data perfectly, we're constantly pruning and forgetting details that aren't useful anymore.
So PaTH gives you this incredible adaptive path of memory.
But memory can become overwhelming. It can be distracting. Fox adds a controllable forget behavior right on top of path tracking.
So they're a dynamic duo.
They really are. Path tells you exactly how you got here, and Fox lets you rationally decide which parts of that long journey don't matter anymore for where you're going now.
So if we connect this to the bigger picture, why does better state tracking matter outside of just building, slightly better chatbots?
This is where that term primitive comes into play. If path is a genuinely new way to encode sequence and structure, its biggest impact is going to be in structured scientific domains, places where the sequence is the meaning.
Okay, like what?
The most obvious one is biology.
Proteins and DNA.
Exactly. They're defined by these incredibly long, complex sequences. The function of a protein, how it folds, is entirely dependent on the specific sequential relationship between thousands of amino acids.
And one small change can have a massive impact.
A huge impact on the protein's final state. Traditional models just struggle to maintain that integrity across huge biological sequences. PaTH's ability to track these long-range, evolving relationships could be a game changer for how AI models analyze these structures.
Predicting folding patterns or determining the impact of genetic mutations?
Things where state tracking is absolutely non-negotiable for accuracy.
So what does this all mean for the future architecture of AI?
I think it's part of a much larger search.
This research, it isn't just an incremental update. It feels like it's part of the global hunt for the next primitive.
Yes, the next foundational building block.
The thing that succeeds what we've relied on for years, convolutions, recurrence, and the original attention mechanism itself.
Right.
PaTH seems like a successful attempt to increase what models can fundamentally represent and reason about, specifically that complex sequential logic, without forcing us to abandon the speed and scale that made the transformer so dominant.
It's an architectural upgrade that doesn't demand a practical sacrifice.
So to sum it all up for the listener, what's the key insight?
The key insight is that path attention is a shift away from memory by measure and a shift toward memory by journey.
I like that.
It transforms positional encoding from a simple, static distance metric into an evolving, content-aware pathway using those data-dependent transformations. It ensures the model's understanding of where a word is located is inherently tied to what happened in the sequence leading up to it.
And that journey leads us to a really intriguing final thought. It's about control. The combination of PaTH and Fox, the ability to precisely map how meaning evolves, and then critically, the ability to selectively forget irrelevant paths that changes the game.
It makes it much more active.
It does. So if AI can not only remember the exact trajectory of meaning, but also master the art of efficiently letting go of older, unnecessary data, does that bring us substantially closer to mimicking the nuanced, adaptive focus that defines human cognition? What happens when AI truly masters the art of productive forgetting?
That's a big question.
That's the big question this research leaves us with.